One of the important steps in using digital gates and circuits is digital circuit simplification. The benefits are that digital computers contain many circuits that implement Boolean functions. The simpler the Boolean, the smaller the circuit. Simpler circuits are less expensive, consume less power, and they run faster than more complex circuits. With this in mind, we want to reduce our Boolean functions to their simplest form. There are Boolean laws and identities to allow this simplification. The goal, then, is to use fewer gates to get the same performance. Our process includes verifying that we know how to do truth tables, building the function out of physical gates, and learning the rules to simplify the digital formulas and circuits. Like common arithmetic, Boolean operators have rules of precedence. The NOT operator has the highest priority. The AND operator always is performed before the OR operator, which has the lowest priority. For example, if we look at a function of x, y, and z, x and not z, or y, there are 3 variables. So 3 bits allows up to 8 different inputs, 0, 0, 0 to 1, 1, 1, provides us with 8 different possible input combinations. Then we build the function and check that the outputs are correct. We begin by taking the 0 and inverting all the values, 0 to 1 and 1 to 0. We AND the not z function. X and not z gives us 4 zeros, 1, 0, 1, 0. Then we OR the output of that with the y row to get our final column, inverted z and x or y. We can build this logic by first building an inverter for the z input and that x with the not z, and take that result and OR it with the y function. It is often helpful to label the intermediate outputs when drawing or evaluating a logic circuit. So for example, if we look at this function, we see that we have A or B. The second function is the NOR function, C nor D. The other way to say that is C or D inverted, or not the function C or D. And then combine those in a NAND gate, which is NAND, the function A or B, and the NOR function C nor D. Then we look at some Boolean laws and theorems. Remember that the Boolean addition is an OR gate, that the Boolean multiplication is an AND gate that can be represented as x and y, or simply x next to y. Let's start with 6 basic laws for Boolean arithmetic. The commutative law for addition and the commutative law of multiplication, the associative law of addition and the associative law of multiplication, the distributive law, and the double complement law. Beginning with the commutative law of addition, the commutative law of addition tells us that we can OR A or B, gives us the same result as if we OR B or A. The order in which the inputs is provided does not affect the output function. The commutative law of multiplication tells us that we can AND A and B, get the same results as if we AND B and A. The associative law of addition tells us that the grouping does not matter. If we OR A or B, take that result and OR that with C, we will get the same function as if we OR B and C, and then take the output of that and OR that with A. The associative law of multiplication tells us again that the grouping does not matter, that the grouping of the ANDed functions tells us again that the grouping of the ANDed inputs does not matter. We can take A and B and AND that with C. Alternatively, we can AND B and C and AND that result with A and get the same value output. The distributive law tells us that we can take A ANDed with B or C, and that gives us the same result if we A and B or that function with A and C. In other words, X equals Y. The distributive law, in another form, tells us that we can take the A or B and that function with C or D to get A and C or A and D or B and C or B and D. Then we look at the double complement law, which tells us that if we have A inverted twice, we get our original value. If we start with a 0, it becomes a 1 and goes back to 0. If we start with a 1, it becomes a 0 and then it goes back to 1. If you would invert a bit twice, you end. In theorem number 2, we find the null law, and the null law tells us that if we AND A with a 0 input, the output is always a 0. If you AND A with any function that is a ground, you get a ground out. The identity law tells us that if we OR A with a 0, the output is the original input. The identity law for multiplication tells us that if we AND any function with a 1, we get out the original function. If we input a 0, we get out a 0. If we input a 1, we get out a 1. And then we have the null law. The null law tells us if we OR any function with a 1, we always get out a 1. Then we start on the idempotent law, the OR form. A or A is always A. So 0 or 0 is a 0, 1 or 1 is a 1. You can follow these two roles of the OR gate truth table. If you OR any input with itself, the output is the original value. And it also applies for the AND function. If you AND any input with itself, the output is the original function. So A ANDed with A, if it's a 1, gives us a 1. If it's a 0, gives us a 0. The inverse law tells us that if we OR A with its complement, we always get a 1 out of the system. If A is a 1, its complement is 0, the output is 1. If A is a 0, its complement is 1, the output is 1. Or any input with its inverse, and the output is always a 1. And the inverse law for the AND function, if we AND any function with its inverse, the output is always a 0. 1 and 0 is 0. 0 and 1 is still a 0. Any input ANDed with its inverse, the output is 0. Then we have the absorption law. The absorption law indicates that if we have A ANDed with A or B, we get back the A function. If we begin with A and a B, we look at the OR combination A or B. When we AND that with the A function, we notice in the truth table that we get back to the original A function. This means that we can simplify the expression quite a bit. In the OR form, we can say A or A and B gives us back the original function A. And again, we can look at a truth table. If we take A, perform the function A and B, and then finally take that output to get A or A and B, we find that the output is the same as the original input A. Again, a significant simplification. We have two more, De Morgan's law in the OR form and De Morgan's law in the AND form. De Morgan's law in the OR form tells us that if we have A nor B, in this case X nor Y, that becomes the same as not X and not Y. In the AND function, or NAND, X NAND Y, that is X and Y inverted, is the same as not X or not Y. Sometimes a shortcut that is used is the phrase, break the line and change the sign.